All right. So for this one, how many proton and carbon NMR signals? Label them and include predicted frequencies. So again, this molecule has symmetry. So that's one of the things you want to look for is, are there places where a molecule is a mirror plane? So in this one, they had four H's or four types of H's, A, B, C, and D. And four types of carbons, 1, 2, 3, and 4. And then frequencies are just predicted from the chart that you'll be given during the exam. So A, because these are next to the oxygen, these are a little farther downfield, 4.5 to 2.5. B is farther away from stuff, so it's saturated, 1.5 to 0.5. D is vinyl, so 6.5 to 4.5. And then C, because it's next to the oxygen, and D, I put it about 5. It'll be kind of additive there. So, but if you put a range there, that's fine. That's all I'm looking for is you can use those tables. Now for this one, the best way to do this is to do process elimination. So one of the things you probably notice right away is there's an alkyne stretch, a triple bond stretch of some sort. So that would automatically eliminate A. All right, so I'm not sure if it's an alkyne or if it's a nitrile. All right, so it could be, a triple bond. The triple bonds come in two fashions. They come in internal and terminal, or a nitrile. But I know for sure it's not A because A doesn't have either of those things. I know it's not C or E because these should have SPCHs. And there is no SPCH. There is no peak at 3300. So it can't be either of those two because of that, right off the bat. Can't do it. There is no SPCH at 3300. So what's left, right? You have two nitriles. Definitely have the carbonyl. And then the question is, does it have the benzene ring? And you see these two peaks here. Show you that's a benzene ring. So that's why the answer is D. For number 3, this is just really asking kind of, again, do you know the difference between a terminal and an internal alkyne? So you got to be able to draw them both, with the correct bond angles. And then just remind us that the key thing about IR stretches is that you need to have all the stretches for the functional group, right? So both internal and terminal have a CC triple bond stretch, but only the terminal has the SP hybridized CH stretch, but it has those two things. So if you don't have the SPCH stretch, you can't have a terminal alkyne. You can still have an internal one or a nitrile, quite frankly, right? So you got to really know that it has to have both those things, right? So one of the examples is carboxylic acid. If you have the OH but not the C double bond O, it can't be it. If you have C double bond O but not a big broad OH, it can't be a carboxylic acid. You have to have both functional groups for that. For 4, this is just literally reading the handout. Literally just taking a look at this handout and be able to identify these things. So nothing hard there. Some of them give ranges, some of them have two things. Just make sure you know how to use that handout. That's all this was for. So for this alkene to practice, this is a tri-substituted alkene. So you got to look on your thing, right? How do I know it's tri? It's because there's only one H here. So it's 1, 2, 3. So it's tri-substituted alkene. So I got to find the tri-substituted alkene. And it says tri-substituted alkenes from 840 to 800. So that's the range for the tri-substituted alkene. This is a di-substituted trans alkene. So the trans alkene is 980 to 960 and so on. It's doing that. This one's a di-substituted terminal alkyne. So it's di-substituted 1, 2, but it's CH is in the end. That was 890. This is a mono-substituted alkene that is terminal. So it's 990 and 910. This is 990 and 910. So it's different than a range. That's two things. Let's see. This is a cis. The cis was 730 to 675. And this one was 890. Right, so just being able to identify tri, di, all those kind of things, cis and trans. Should be able to do that, but now you have IR stretches for them. So these two are examples of things that don't have any symmetry, right? There's no way to cut these to have symmetry. So most molecules that don't have symmetry will have a lot of have more peaks than you'd expect, or have lots of peak that you normally would expect. And that's all this is. Biggest thing for HNMR, make sure you draw on the H's. That helps. Carbon NMR, don't forget the H's that don't have, don't forget the carbons that don't have any H's. Those ones we tend to forget, and also don't forget the OH. But this one doesn't have any symmetry, so don't try to find symmetry where there isn't any symmetry. Similar type of deal here, using those tables. This one's asking for integrations. I won't ask for splitting because we didn't really cover that in class. So the number of signals is just number of different types of peaks. So there's 3 types, A, B, and C. Relative integrations. A has 9 hydrogens, they're all the same. B has 1, C has 1. And then the frequencies, again, these are just using those tables. Just estimating a range, 1.5 to 0.5, because these are saturated. And then these are both off the alkene, they're vanillic. So 6.5 to 4.5. Just estimating a range. But again, no symmetry here. All right, for this one, I didn't draw it out, but hopefully at this point people can do this already. This is very similar to ones we've done. First step is going to be numbering the atoms. Numbering all the atoms. Add lone pairs throughout. Add lone pairs. Label bonds broken and formed from starting materials or products. So I'm not asking for each step of the way, but I'm saying if you look at this and you look at this, what bonds are broken, what bonds are formed. So broken C3 to S2, that bond is gone. OH, O7 to H is gone as well. New bonds that are formed, C3 to O7 and S2 to H. Those are the kind of things I wanted. Again, have the steps labeled there for you. First step's proton transfer, add, proton transfer, limb, proton transfer. We've done this quite a bit, hopefully. I'd give you more space, obviously, but I just want to make sure we got the ideas here. Be able to take a chair structure and make it a wedge and hatch. Be able to take a wedge and hatch, make it a chair structure. Pretty self-explanatory. Got to be able to draw the chairs well. Bond angles are really important. Make sure you get those correct. These are all pointed up, so I drew them all wedged. There you go. This one, 4 are down, 1 is up. So you can see how I drew it here. There, you could have drawn these all hatched. That'd been fine. You could have done this in a different chair. Been fine as long as these 4 were down and that one was up. There's different ways to do it. What doesn't change, right, is, remember, when I look at a flat structure, wedges and hatches doesn't tell me what's axial or equatorial. All right, this could be axial up or equatorial up. Depends on how I draw the chair, right? So it doesn't tell me that by looking at this or this. All right, so you make a choice on how you want to draw it. As long as you remember, if something's up, it stays up. If something's down, it stays down. So if I wanted to draw, this is another way you could have drawn this thing, would be like, this would also be correct, right? It's just the ring flip version of this one. So I pulled this down, pulled that up. So now this is, instead of equatorial up, it's axial up, and everything else is still down, but I've switched from axial to equatorial. So you could draw it this way too, it's fine. Doesn't matter. Here we go, given the steps, proton transfer, addition, proton transfer, elimination, addition, proton transfer. First step is proton transfer to CH+, it reacts, it always reacts with something double bonded, like oxygen or nitrogen, so we protonate there. Oxygen then adds, that breaks the pi bond, 2 steps. All right, we balance our charge, we're going to be at overall plus charges. Do a proton transfer. All right, we're trying to put the nitrogen here because, again, that's where it's going. We do an elimination. That kicks off the NH3, which we've made there. We make that oxocarbenium ion. This oxygen comes around, does the addition, breaks the pi bond. Then a final proton transfer, deprotonation is the last step. Again, good numbering systems help to make sure where things end up and to remember what you're trying to get done, right? You can always write down what bonds need to be broken and formed from starting materials to products. It helps give you an idea of like kind of where you're going. All right, so for this one, we're in neutral condition. So a lot of times you see H plus with the catalyst, so it's acidic condition, so you have an overall plus charge. But here we have a neutral condition, so there's no charges to start. Still, the steps are addition, proton transfer, elimination, proton transfer. So the first step is going to be the nitrogen is the nucleophile. It has a lone pair, the oxygen, the carbon of the carbonyl. We're going to add. You're going to make a negative charge and a plus charge. You're going to do a proton transfer to get rid of those two charges. So the negative charge takes the H, gives the electrons to the nitrogen. Then we're going to do an elimination, which is going to leave a new pi bond. We lose the O minus. The O minus then takes the H, does a proton transfer, and we get to the two products. Yes, you do need to do this proton transfer. You need to eliminate the charge. Notice you go, when you're under neutral conditions, you go from no charge to charge, no charge to finally no charge. You kind of go back and forth for those things. So be careful when you have neutral conditions. So this one actually talks a little bit about, you have two options, A and B, and it's kind of asking you, the mechanism is addition and elimination. So you add, break a pi bond, then make a pi bond again. And you can see the chlorine is the leaving group in both cases. You have two nucleophiles. And so you could do the mechanism, add, elim, right? So both products, so two mechanisms. Which one's more reactive, A or B? A is more reactive because it can't do resonance. And then which product is more likely? Well, then C is more likely because the most likely product comes from the more reactive starting materials, right? If something reacts, that's the kind of product it's going to form. So A is the most reactive because it can't do resonance, and C is the most likely product because it comes from more reactive starting materials. Sometimes we get confused on that kind of stuff.